Hi everyone, welcome to another video for research design and analysis. In today's video we're going to be talking about analysis of covariance, which is a special case of the general linear model where we're mixing continuous and categorical predictors. As you'll see, this is a lot like factorial analysis of variance that we've discussed in previous modules, but the difference is that now we're going to be controlling for a covariate in order to get a clear sense of what our categorical factor is doing to the dependent variable. So an important use of the analysis of covariance is controlling for critical individual differences in the data. So I think a good kind of question to start with is, what makes people different? In an experiment, right, usually the key manipulation that we're interested in is the independent variable, but not everyone is going to have the same response to that treatment, nor is everyone going to enter into your experiment kind of in the same place. So in an ideal situation, our manipulation would be the only difference that we have to contend with. And it would basically be, what we measure in the data, and then error would just be any measurement error that were in the data. But we know that that's not the only, or I should say, we know those are not the only factors at play. There's not only going to be the treatment effect and measurement error, but there are going to be real individual differences based on the characteristics that any subjects or participants come into the study with. So in order to understand the effect of the independent variable on the dependent variable, it's oftentimes helpful to remove other sources of variability from the dependent variable. And in analysis of covariance, that's what we're really going to try to do. We're going to try to remove some variability in the dependent variable to get a, you can kind of think of it as a cleaner assessment of what the independent variable is doing in our data. So let's think about an example where we have a hypothetical teaching intervention. So we're looking at some scores on some knowledge assessment, and we have two different curricula. We have a traditional or kind of control curriculum, which is coded as -1, and then we have a experimental curriculum, which is coded as +1. And if we're just analyzing these post-test scores, right, you can see, okay, the students who took the control curriculum tended to score worse than the students who we're in the experimental curriculum, but there is a fair amount of overlap in these data. So one way to analyze this question would simply be to do an analysis of variance or an independent samples t-test and compare the scores from these two different classrooms. However, right, one of the issues in good experimental design would be what knowledge did those students have coming into this situation and when they were randomly assigned to each of these two different curricula. So ideally, we'd actually have a study where we have both these post-test scores and pre-test scores. And so now that's going to make the situation a little bit different. But you can see in this scatter plot here, we're looking at the post-test scores on the y-axis as a function of the pre-test scores on the x-axis. And there's some evidence of a linear relationship there, right? As people scored higher on the pre-test, they also tended to score higher on the post-test. And then we're color coding their individual dots based on the curricula, where again, -1 is sort of the control or standard curriculum, and +1 is this experimental curriculum. So you can see that there are now different sources of variance in terms of people's ultimate scores, right, or where they end up. You can look at the vertical shift between the yellow and the blue dots. That difference is reflective of our treatment, right, the actual effect of receiving these two different curricula. However, there's also variance that's being explained by what your pretest score was, right? For all these levels of post-test score, if you had a higher pretest, we expect you to score higher. If you had a lower pretest, we expect you to score lower. So there are multiple sources of variance tied up in these pretest or in these post-test scores. So what we would really like to do is isolate the effect due to our treatment as best we can in order to have the most statistically powerful test of our intervention. So a good way that we can do that is through what's known as an analysis of covariance, where in essence what we're going to be doing is controlling for a person's pretest score and then saying, if you received the experimental curriculum, did you tend to score better than people who received the control curriculum? And you can really think about this, right, in much the same way we have other multiple regression models, because the analysis of covariance is just going to have one predictor that is your pretest and one predictor which is the curriculum that you received. And what that will allow us to do is then say, right, as opposed to these marginal distributions over here where we ignored pretest, right, and we just said, okay, is there a difference in scores between the two curriculum? What controlling for pretest will allow us to do is say, okay, given where you scored on the pretest, right? Is there a difference between the experimental and the control curriculum? Because remember, another way of thinking about controlling for a variable is saying holding that variable constant. So for a given level of pretest, let's say that the score was 48, how different do we expect these two groups to be? If the score was 52, how different do we expect these two groups to be? And you can think about how we're removing the error here, and we'll get into more detail about it in a second, but you can think about how we're removing the error here by comparing the standard error around this regression slope here to the variability in our density plot here. If we're not accounting for pretest, all of the variability within this group that's actually explained by what your pretest score was just gets lumped into the standard deviation, right? Similarly for the control group, all of the variability in this group that could be explained by what your pretest score was is just getting lumped into the standard deviation. So we're making our data look more variable than they actually are if we ignore the relationship between post-test scores and pretest scores. So how do we actually achieve this in practice? Well, let's step back a second and think about just the factorial ANCOVA example without controlling for pretest, right? The idea would be that in our y variable, in our dependent variable, we have a sum of squares total, and some of that is getting explained by the effect, right? Or that's the sum of squares explained by the regression, and then the rest of that will be residuals, or a sum of squares of the error term. Right, so we would have, okay, there's some effect, and then there is variability that remains unexplained, and all of this would add up to the total sums of squares in that factorial ANCOVA. We can contrast this to the ANCOVA, where what we're going to try to do is partition that total sum of squares into the variance due to the effect, the variance due to the subject, and then anything left over, right, is the error term. And so this SS subject, it really, is going to be anything about the subject that's explained by the covariate. I labeled it as SS subject here because the idea is we're trying to explain individual differences and capture some important characteristic about that subject. But we could equally, label this as SS baseline or SS covariate, right? But the idea is we're going to try to shrink our error term by explaining some of that variability away. And then what we can do is get a more powerful f-test, because over here, if we're not accounting for those differences at baseline, what we find is that we're dividing the mean squared error for the effect by the mean squared error of the residuals, right? And that's going to obviously be much bigger if everything is getting lumped into our error term. However, if we correctly recognize this, right, as the variability due to which subject you are, or the variability due to baseline, then our error term is going to get proportionally smaller, because the unexplained variance now is this part over here. And now when we actually go to calculate this F ratio, we're again going to have the mean squared error for the effect divided by the mean squared error of the residuals, but this mean squared error of the residuals is after we've accounted for these baseline differences. So the sum of squared error is going to get smaller, which is going to make the mean squared error smaller, which is ultimately going to make this F observed larger, everything else being equal. So if we can account for those baseline differences, then we can potentially get a much more statistically powerful test of our hypothesis and see if our intervention had any influence. So this is what we're doing when we're conducting an analysis of covariance. It's otherwise very, very similar to an analysis of variance that we've looked at before, where we have some sort of categorical factor and we want to look at its influence in our dependent variable. But what we're going to do now is include some kind of continuous covariate. So for instance, in our example with the teaching intervention, we're going to have the sum of squared errors for some effect, which is did you receive the experimental curriculum or the control curriculum? And then we're going to control for a continuous variable, which was your pretest, your baseline score of knowledge before you were randomized to one of those two conditions. So that way we're accounting for the knowledge that subjects came into the intervention with, pulling that out so that we can more clearly say, okay, well, how much variance did we explain compared to the amount of variance that remains unexplained? So in conducting this analysis of variance, we have a few different situations because we're in essence conducting a multiple regression, right, where we have a continuous covariate and we have a categorical factor. But remember, when we do multiple regression, one of our concerns is how do our variables correlate with each other? So the relationship between our covariate and our grouping variable is going to be really critical here. Because what we would like to know is about the total variance in test scores, we want to look at the variance explained by the curriculum, right, what we've assigned people to, compared to the residual variance, that error variance that is left over. Now, in an ideal situation, our covariate is not correlated with this independent variable, right? This is some baseline characteristic of the participants that is not associated with the treatment because we've randomly assigned people to the different conditions. So this covariate is independent, right? It is uncorrelated with the treatment. It is, however, going to be correlated with the outcome because we want this covariate to be associated with the outcome in order to explain this error variance. So the more correlated the covariate is with your dependent variable, the larger the total sum of squared errors will get explained by the covariate, which ultimately means then the error variance is going to get smaller. Now, this is the ideal situation, but it's not always the case because usually there's going to be some amount of correlation between the covariate and your independent variable, right? So this is the same as collinearity that we talked about in previous multiple regression examples. We'll have one x variable, the covariate, that is correlated with our second x variable, which is our treatment factor. Now, if this correlation is pretty minimal, then we're okay and we're still reaping the benefits of this situation because most of what the covariate is doing is just reducing residual variance. However, as the correlation between the covariate and the treatment variable gets larger, that's going to be a concern. So that isn't as much a problem in large randomized controlled trials because you're randomly assigning participants to the different groups. So hopefully, any differences that arise in those groups due to chance are pretty minimal. It can be a bigger problem if you have small samples and random assignment isn't going to completely balance everybody on all of their baseline variables. And it can also be a problem, for instance, in cohort studies where people are coming into your study with different conditions and you're not randomly assigning them to groups. So as with any multiple regression, the larger that correlation between the covariate and the categorical factor becomes, the more we have to be concerned because their shared variance is going to get excluded. And as we've talked about in previous videos, that can significantly alter our interpretation of those x variables. So let's come back to our example with the teaching intervention. So in this case, if we wanted to analyze our data using a factorial ANOVA, we'd have our post-test scores as a function of some intercept plus a slope times a contrast-coded variable that tells us, which curriculum you received. And if you actually do this, in this case I did this in Jamovi to get this ANOVA table, but we can look at the sum of squared errors explained by the regression. And in this case, because there's only one effect in our regression model, the sum of squared errors explained by the effect of curriculum is redundant with the sum of squared errors total. And those both have explained 422.5 squared errors with a single degree of freedom, which gives us a mean squared error then of 422.5. And then to calculate the F ratio, right, we also have to get the residual sum of squared errors. So out of our original total, which was 1,218, our residual sum of squared errors was 795, right? So that's the total amount of error that is left over after accounting for which treatment you received. That had 38 degrees of freedom. We could calculate a mean squared error for those residuals, and then the ratio of the mean squared error explained to the mean squared error of the residuals in this case happens to be 20.2. So we have an F value of 20.2, which is a pretty large effect because what we're saying is the variance explained by which curriculum you received is about 20 times larger than what the residual variance per parameter. Now, let's consider this if we actually treated this as a factorial ANCOVA. So in an ANCOVA, what we're going to have, right, is the same dependent variable, our post-test scores, but now in addition to the effect of curriculum, we want to control for what people's baseline scores were. So this is going to make our analysis of variance table a little bit more complicated. And one of the first things you'll notice is that our sum of squared errors for the regression total is much larger. We're now explaining 784 squared errors as opposed to 422. Now, the 422.5 is still there because that is the effect of curriculum. That is what is getting explained by which curriculum you had. But we're also explaining variability based on what your baseline scores were. Right? So now we're accounting for not only what curriculum you were randomly assigned to, but we are also accounting for what your baseline score was when you came into the experiment. And the net effect of that is a statistically large reduction in the error. And we can see that clearly in the residuals, right, where before we had 795 squared errors unexplained. Now we only have 433 squared errors unexplained. So as a proportion of the total, we've explained a lot more of the variance here. The other thing that you'll notice as we kind of work our way across, right, get the degrees of freedom, get the mean squared error, and then get the F value, this F value is now proportionally a lot larger because we reduced the residual variance by so much. This F value is the mean squared error of the effect over the mean squared error of the residuals, right? So in this case, the mean squared error of the residuals is 795 divided by 38. So that's a relatively large mean squared error. Whereas over here, it's 433 divided by 37. So even though our degrees of freedom have gotten smaller, the residual sums of squares have gotten way smaller, with the net effect of making the F observed for the effective curriculum a lot larger. Now, this gets back to what we were talking about at the beginning of the video, right? What was originally just lumped into the error term is actually an individual difference, right? Is a characteristic of people's baseline scores. And now we are explaining that. So it moves out of the unexplained variance and into the explained variance. And now our unexplained variance is much smaller, which makes our f-tests proportionally a lot larger if everything else stays the same. So by controlling for those baseline differences, we actually have a statistically more powerful test of our treatment, and we can see that there does seem to be a difference here due to what curriculum you received. Now, why is ANCOVA useful then? Well, this ability to remove variance from our error term is really powerful. And the idea, right, is that in ANCOVA, we're interested in the same things that we were before when we were talking about analysis of variance. We're interested in potential differences between, two or more groups. The difference between the control and the treatment group, or the placebo, the low dose and the high dose group, right? Any sort of categorical factor we might be interested in investigating. But now what we can do is we can mix in continuous variables that help to explain some of the total variance. And whereas before this variability was remaining unexplained and getting lumped into the error term, if we can account for it through the intelligent use of covariance, now what we're explaining with our effect is proportionally much larger relative to what remains unexplained. So when the assumptions of our ANCOVA are met, we can remove the variance that is shared between the dependent variable and the covariate, and this in turn is going to reduce the unexplained variance and make the explained variance then look proportionally a lot bigger. But it's important to note that this is when our assumptions are met, and we have to be careful in our use of covariates. We don't want to randomly throw in covariates or add covariates that are associated with our independent variable, because that can potentially reduce our statistical power. And this leads to a consideration that we talked a little bit about before, but I want to elaborate on now. Right, so ANCOVA can be a very useful technique for improving statistical power relative to analysis of variance. And as we've explained, right, that's because variance explained by the covariate gets pulled out of the error term, and now it's explained variance, which makes the denominator of our f-test smaller, which means given the same reduction in error here, we're more likely to have a statistically significant result. Right? Essentially, we've removed variability that was previously over here to improve our ability to make inferences about the treatment effect. Now, the problem, as we said, is that if our covariate is actually correlated with our predictor, right, then we're going to have collinearity in our multiple regression model, and the shared variance between these two is going to be removed. So if the correlation between the covariate and the categorical factor is small, that's not a huge deal, right? It's a manageable amount of collinearity. But as that correlation between the covariate and the categorical predictor gets higher, remember that we're excluding the shared variance from this calculation, so we're also somewhat working against ourselves, right? We do reap some of the benefits of the ANCOVA because we are removing error variance, but we're also removing variance from the predictor itself, and that's not what we want to do in an ideal situation. So we need to be careful here because when used correctly, this can really improve our statistical power. If used without careful consideration of the relationship between all these variables, this can not only lower your statistical power, but it may spuriously alter the effect of the independent variable. So if you don't really realize that when you have a correlation there, it impacts the independent variable, right? You might make a poor decision about which covariates to include, and then you might make a poor decision about the effect of your independent variable on the dependent variable. So you really need to carefully attend to the relationship between the independent variable, the dependent variable, and the covariate before you just jump into this analysis. So you can go down a rabbit hole with this consideration, so I'll try to summarize this briefly. But the main thing is that we generally want independence of the covariate and the categorical factor. This doesn't always happen, and it's not always a problem, but it's generally desirable. One common situation, though, where this gets violated is if we have baseline differences between our two groups. So like we said earlier, we'll generally randomly assign people to conditions, and then hopefully they won't really differ, or I should say the covariate won't really differ between the two groups. Like if it's pretest scores, right? Our experimental group and our control group should have approximately the same pretest scores if they've been randomly assigned. That's not always the case, though, right? And sometimes one group will just happen to have higher scores. So, what if my experimental curriculum already had higher scores? Well, I need to account for that in my analysis. And many people will thus use ANCOVA, to correct for this baseline imbalance between the two groups. So we're trying to account for the fact that, maybe random assignment failed, or for whatever reason, one group happens to already be higher on the dependent variable at the start of the experiment. So statistically, this works. But remember, right, this is a multivariable regression, and we're doing a type 3 sum of squared errors calculation. And if you don't remember what those terms mean, you can refer back to some of our previous videos, right? But the main thing is to take into account that if the covariate is correlated with the independent variable, their shared variance is getting excluded. So mathematically, right, we can do this and in essence correct for that baseline imbalance, but it's not as simple as that, right? We can't just say, we've controlled for baseline and therefore we have a perfect, unbiased, accurate representation of the effect of our treatment. And I won't delve into the full complexity of the issue here because it's a little too big, but there are some things that you should keep in mind. First is that you can run an analysis of covariance when groups differ at baseline, and this can give you unbiased estimates of your treatment effects. It is important to check some of the other assumptions that we'll talk about in a moment. But this definitely can be done. And ANCOVA is generally going to be preferable to other methods of adjusting for baseline. So sometimes people say, well, you should calculate change scores or like a proportion or percent change score instead of doing this analysis of covariance. And that's almost never better, and in some situations worse than the ANCOVA for a lot of the inferences you might want to make. So in general, if you do have these differences at baseline, ANCOVA is a useful way of controlling for that. However, I think it's important to point out that you do not want to select covariates based on statistically significant baseline differences. You want to select your covariates based on the magnitude of the relationships between the covariate and the DV and the independent variable, and you want to select your covariates based on an irrational analysis of these constructs and how they're all supposed to relate to each other. Theory should give you a better indication of what covariates you need to control for. Don't rely on statistical significance to make that decision. And again, without getting too much into it, a big part of the reason you don't want to rely on statistical significance to make that decision is that you might find, well, hey, there's no significant baseline difference in this covariate, therefore I won't control for it. But a lack of statistical significance might be more just a reflection of your sample size and that you weren't actually powered to detect it. So you shouldn't really use statistical significance when you're considering what covariates you want to include in your model or not. The second consideration that we need to make with analysis of covariance is that it is just a special case of the general linear model where we're adjusting for a continuous covariate in order to test the effect of our categorical factor, right? So if you from our teaching example, right, we're looking at post-test scores as a function of an intercept, a slope times your baseline, and a slope times your curriculum. And when we really write this out and think about it as a multivariable regression, one thing that should be apparent here is that there's no interaction term in this model. We're just looking at two main effects. So implicit in this analysis of covariance model is the lack of an interaction. The other way that people talk about this is as homogeneity of regression slopes. So often in textbooks on ANCOVA or in statistical packages that show you how to do ANCOVA, they will have some test for the homogeneity of regression slopes. And in general, you want this assumption to be supported. You want to find that the slope, right, the effect of your covariate is approximately the same at all the different levels of your independent variable. So we can see that more clearly here, right, where we could fit an interaction term, which would allow us to then have a different relationship between post-test and pre-test in each of our two groups, right? Because this interaction term would allow one slope to be estimated for the experimental curriculum and a slightly different slope to be estimated for the control curriculum. And visually what you can see is that these slopes don't look that different. These slopes look homogeneous across the two different levels of our independent variable. The effect of the covariate looks pretty much the same. So qualitatively, this looks like the homogeneity of regression slopes assumption has been met. To formally test that, however, what you would need to do is actually look at this interaction term here and see, okay, what is the actual magnitude of the effect, and is it statistically significant? And by and large, the way that people assess homogeneity of regression slopes is by looking at this interaction and then deciding, is it statistically significant or not? And if it is not, then we would say, well, we didn't find any evidence that the regression slopes are different, therefore we feel reasonably comfortable that they are homogeneous. But I think, again, a visual inspection of this is important because that really drives home what the idea is. If this interaction is trivial, then the slopes between these two groups should be about the same, which means you can get away with just having the two main effects in your model, and the interaction can more or less safely be ignored. So I know that's a lot with respect to analysis of covariance, but I think it is nice in that analysis of covariance really builds off of a number of things we've already discussed, which is multiple regression where we have continuous predictors, right, and factorial analysis of variance where we have multiple categorical predictors. And all we're doing in ANCOVA is mixing the two together, where we're going to have a continuous covariate and a categorical factor, and then we're going to make some assessment to see, okay, is there relative homogeneity of the regression slopes? And if that assumption is satisfied, then this is a really efficient way of analyzing your data. For instance, when you have a randomized controlled trial and participants are randomly assigned to different groups and then assessed over time, or even in non-randomized cohort studies where, maybe rather than treatment versus control group here, this might be smokers and non-smokers, or concussed versus non-concussed individuals, right? You could have non-random assignment to groups here as well, but the idea would be that you have some continuous covariate, some categorical factor, and by choosing your covariates wisely, you can get a much more powerful test of the relationship between this categorical factor and your dependent variable.